Alright, so you may wish to pause the recording at this point in order to read the problem statement and come up with your own strategy for a solution. Alright, so this is actually one of the most common air conditioning processes that you'll come across. That is the cooling of moist air below the dew point temperature in order to extract moisture from it, and then reheating that same air back up to a comfortable temperature. In this process, this problem, we've been asked to do several things, the first of which is to sketch the process on a psychrometric chart. If you can do this, you can't always do it, but if you can do this, I highly recommend that you do, because this will give you a visual way of understanding that you can fix the various state points in a psychrometric conservation type problem. Okay, so here we can actually put two of the points on the chart directly. State 1, where with the temperature of 40 degrees and relative humidity of 40%, I can stick straight on the psychrometric chart. So notice that the dry bulb temperature is the x-axis, and the relative humidity is 40%, is that line corresponding to point 4, the curved line going up and to the right. Those are lines of constant relative humidity. State point 3 can be fixed similarly. So there we are at 25 degrees C, and a relative humidity of 50%, which I eyeball in between 0.4 and 0.6. By the way, this psychrometric chart that we have in this problem is just for illustrative purposes. I would not use this actual chart in order to take numbers off of. I'd use a more detailed one. But in any case, there's state points 1 and 3. State point 2 takes a little bit more thought. So the way I went about this was to think about the process going from 2 to 3. 2 to 3 is the addition of heat transfer. There's no addition of moisture. There's no subtraction of moisture. So the amount of water does not change. And if the amount of water doesn't change, the amount of water per pound mass of dry air, or kilogram of dry air, cannot change either. The humidity ratio from 2 to 3 must remain constant. If I'm extracting moisture from state point 2 at saturated conditions, having cooled it below the dew point temperature, 2 must be on a straight line, and 2 starts at a phi of 100%. So there's state point 2. Going from 1 to 2 is a little tricky. So from 1 to 2, before I've cooled it down all the way to the saturation point, the humidity ratio can't change. So 1 to 2 initially looks like that. Eventually, it gets below the dew point temperature, and then it follows a constant relative humidity line from the end of 1 down to state point 2. Okay? So in this process, the important points really to know are where 1, 2, and 3 are respectively. The fact that 1 goes to 2 via a constant humidity ratio process first, and then sticks to the humidity or the relative humidity of the 100% line all the way down to 2 is not as important as knowing where 1 and 2 and 3 are individually. But in any case, there's part A. There's our psychrometric diagram. Notice that points 1, 2, and 3 on this diagram fix the state at points 1, 2, and 3, and I can really read off any property I want. Okay, so part B asks us to find the mass flow rate of dry air in kilograms per minute. I've been given the volumetric flow rate of the dry air at state point 1. In order to find the mass flow rate of dry air, I simply multiply by the density of dry air. Or recognizing that density is 1 over specific volume, I just need to calculate the specific volume of the stuff at state point 1. So, volumetric flow rate of the dry air given at 1, need to calculate the specific volume of the air at 1. So one way to do this is to model air as an ideal gas. So V from the ideal gas equation is R of air times the temperature at 1 divided by P of the air. That is not the total pressure at 1. That's only the partial pressure of the air. Remember that Dalton's model tells us that when we have a mixture of gases, that both components, think they see the mixture temperature, and both components think they see the entire volume. But each individual component has its own unique pressure, which is the partial pressure. So I get the partial pressure of the air at 1, I subtract the vapor pressure of the water from the total pressure. The vapor pressure of the water at 1 is found because I know the relative humidity at 1. So I take that relative humidity, multiply it by B sub G, That is the saturation pressure of water at the temperature T1, and then I have enough to plug in the numbers to find the specific volume, which is kind of tedious, which you can see from the resulting calculation. So I had to look up that 7.384 kilopascals, which is Psat at 40 degrees for steam. I had to make sure to use the absolute temperature for T-air, the heat conversions, etc., etc. I get my specific volume at state point 1. Now there's an easier way to do this. The easier way to do this is to recognize that on the Psych chart itself are these lines of constant specific volume. And those are mixture-specific volume per unit mass of dry air. And since the volume of the mixture is the same as the dry air volume, that's just the specific volume of dry air. So the easier way to do this is go, there's state point 1, read a line of constant specific volume off the chart. Here I approximate it between 0.9 and 0.925, is about halfway in between, 0.913, and that's pretty darn close to what my calculation was. So either way, you get your specific volume. To find the mass flow rate of the dry air, you just divide by that specific volume, and you've got it. In this problem, 82.1 kilograms per minute. So on to more exciting things. How much liquid water was extracted in the process? So to give this a shot, let's take a look at conservation of mass for that system in red. Now I've got two different things in this mixture. I have both air and water. So if that's the case, it might be a good idea to look at conservation of mass for each individual component. My conservation of mass for just the air looks like this. It's steady state, so m dot of air at 1 minus m dot air at 2 adds up to 0. There's no m dot of air down at the bottom where the water's coming out. Conservation of mass for the air is pretty boring. Basically what it tells me is that there's only one mass flow rate of dry air. Let's just call it m dot a. Now let's look at conservation of mass for only the water. So this is also a steady state system, but I'd like you to notice the different thing that I've done with the mass flow rate of water. Notice that the mass flow rate of water has been written in terms of the mass flow rate of dry air multiplied by the humidity ratio at 1. So I can take the mass flow rate of dry air at 1, and if I multiply it by the amount of water per unit mass of air at 1, I get the mass flow rate of only the water at 1. So whenever I have a mixture of moist air, water and air together, when I need a mass flow rate of water, that's what I'm going to write. The same thing happens over here at state point 2. That combination of mass of dry air at 2 times the humidity ratio at 2 gives me the mass flow rate of only the water at state point 2. Down there at the bottom, however, that is pure liquid water. It's not a psychrometric mixture at all. I write that as plain old m dot w. Okay, so the moral of that story is this. If you've got a moist air mixture, mass flow rates of water are found in terms of mass flow rates of dry air times humidity ratios. If you have only water, you just write it as the mass flow rate of water. Okay, so solving for the mass flow rate of water, I find it's equal to mass flow rate of dry air times the difference in humidity ratios. The humidity ratio at 1 is known because I know T1 and Phi1. The humidity ratio at 2, not so sure just yet. Okay? So in order to figure the humidity ratio at 2, let's take a look at conservation of mass for the next little section, from 2 to 3. So there's my system. Apply conservation of mass to the air, equally as boring as before. Conservation of mass to the water vapor. Again, writing those flow rates of water in terms of mass flow rate of dry air times the humidity ratio. And now I go, aha! Conservation of mass for the water from 2 to 3 shows me that the humidity ratio remains constant going from 2 to 3. Okay? So I can find the humidity ratio at 2 by knowing the humidity ratio at 3, which is fixed by T3 and Phi3. Of course, when we drew our initial psychrometric diagram, we used this fact implicitly, the humidity ratio not changing from 2 to 3. We can prove that to be true by looking at conservation of mass for only the water from 2 to 3. Okay, so now that I'm here, all I need to do is calculate these numbers for omega 1 and omega 2. Here's one way to do it. Use the formula that gives omega from knowledge of temperature and relative humidity. That takes a little bit of work because I have to, one, do the calculation. Also, I have to look up P sub G at the dry bulb temperature, that is, steam saturated pressure for the corresponding temperature. I can also do that for omega 3, which is the same as omega 2. Again, that takes some doing, but I can eventually get there. So about 0.0188 and about 0.0099 for the two humidity ratios, respectively. Of course, the other thing to do, and the easier thing to do, the thing that I recommend that you do, is pull these omegas straight off your psychrometric chart itself. There's state point 1, go to the right, read omega 1 is 0.0188. There's state point 3, go to the right, read omega 3 off the chart directly is 0.0099 kilograms of water per kilogram of dry air. Either way, you find that the mass flow rate of water extracted from the process from 1 to 2 is just a little under 0.8 kilograms per minute. Now, the savvy observer at this point might realize that I made this a little bit more difficult than I had to. An equally legitimate way to go about this would be to pick the entire thing as my system, in which case my mass flow rate of water could be calculated from conservation of mass of just the water as m dot A times omega 1 minus omega 3 instead. So I could do it directly and get exactly the same answer. I chose to go from 1 to 2 and 2 to 3 because we're often interested in what that intermediate state is. I often like to know what the properties of state point 2 are in addition to just the end state. Either way is perfectly fine. Next, we've been asked to calculate the rate of heat transfer out of the air in the cooling section. So in the cooling section, if that's the cue I want, I have to pick that as my system to apply conservation of energy. Let's look at conservation of energy. So here we go. It's steady state. I have Q leaving the system, so I have minus Q dot out. There's no work in or out of the process. And then I have some interesting looking terms. So one, I have an m dot times an enthalpy term. I have an m dot and enthalpy term leaving the system at 2, and an m dot enthalpy term leaving the system with the liquid water. Okay? So at this point, you're looking at this and going, where in the world am I taking into account that the stuff at 1 is both air and water? It looks like you've only got air in there. Well, that's not the case, because when I'm dealing with psychrometric mixtures, it is implied that any mixture enthalpy is the enthalpy of both the dry air and the water together, but divided by the mass only of the dry air. So both H1 and H2 are the enthalpies that I want of both air and water together, divided by the mass of only the air. That's out of sake of convenience, because in psychrometric processes, the mass of the air usually never changes, but the mass of the water can go up or down, or stay the same, which is what's happening here. For the water leaving at the bottom, however, that is only liquid water, and that is per unit mass only of water. That's a very important point. If you mix up these enthalpies, or you don't understand what they represent, then you will consistently get your conservation of energy incorrect. So this is a very important point to take to heart. In any case, H1 and H2 are both fixed because I know both the dry bulb temperature and the humidity, or relative humidity, at state point 1. And for 2, I know the humidity ratio and the fact that the relative humidity is 100%. It's saturated at state point 2. H of the water is also known because I'm going to approximate that as the saturated liquid enthalpy of just plain water at T2. Well, but wait a minute. Do I know T2? Well, if I rely on my psychrometric chart, then the answer is yes. It becomes obvious to me. So I can read these enthalpies directly off the chart for 1 and 2. It doesn't actually appear on this specific chart, but most charts actually have enthalpy right on the diagram. So I can read that off the chart as 100.8 kilojoules per kilogram of dry air for 1, and 38.9 kilojoules of mixture enthalpy per kilogram only of dry air, directly off the chart. And also notice that at state point 2, I can go down here and read off the chart that the temperature of the saturated air is 13.7 degrees, which means, yes, in fact, I can find the enthalpy of the liquid water as H sub F at that temperature. So I've calculated all of my enthalpies. I can plug those into my Q dot equation and get 4,071 kilojoules per minute. Okay, very good. Now let's take a look for a moment to see how much time the psychrometric diagram was saving me in this problem. Because I could, if I wanted, calculate these enthalpies at 1 and 2 of the psychrometric mixture the old-fashioned way by hand. So, H of the air at T1 plus omega of the stuff at 1 times the H of just the vapor content per unit mass of water at 1, that all added up together is what H1 is. Likewise for H2. So I could calculate this by hand. Let's see how much more work that is. So first off, I have to look up H of just dry air at 25 degrees in the ideal gas tables. I get that number. And then I have to look up H of air at state point 2 at a temperature of 13.7. But if I didn't use a psych chart, I didn't know the temperature of the stuff at 2 was 13.7. So in order to get that, I had to go, what's the temperature at 2? Oh yeah, it's the dew point temperature. Dew point temperature where? At the pressure is equal to the vapor pressure at 3, because that's the same as the vapor pressure at 2. And I can only find that by multiplying the relative humidity at state point 3 times P sub G at T3. I look up those guys. Eventually I find it's 13.7. That was a lot of work. But it gets worse, because once I find that, I also have to look up H sub G for 1, which is the saturated vapor enthalpy at state point 1 for just water at 25 degrees. I look up that number. I do the same thing at state point 2 at a different temperature, and I plug them all in together, and eventually I find my Q dot as I did before. Now there's a huge caveat here. When I go to find H1 as H air 1 plus omega 1 Hg1, and I plug in the numbers that I just told you I looked up, here's what I get. 347 kilojoules per kilogram. And if you're pretty astute here, you're like, no, that's not what I got off the psych chart. You said I got 100.8 kilojoules per kilogram of dry air off the psych chart. Those numbers don't match up. You're right. Those numbers don't match up. Here's why. Because for the psychrometric charts, the reference state for air's enthalpy being equal to 0 is different than the reference point for air's enthalpy being equal to 0 directly from the ideal gas tables. So there's a huge moral of this story. If you calculate H2 minus H1 from the psych chart, you'll get exactly the same number as if you calculate H2 minus H1 by hand. The individual value for H1 from the psych chart versus the individual value for H1 as calculated by hand could and usually will be different. Okay? So that's a very important thing to understand. As a consequence of that, you should never, ever mix a calculation where you get one value for a mixture enthalpy off a chart and another value calculated by hand. You have to be consistent throughout an entire problem. Either calculate all the H's by hand or get all the H's directly off the chart. Usually, not always, usually it's more convenient to get it directly off the chart. So in any case, now that we've got that settled, I think you can probably see your way through the rest of this problem pretty easily. The last thing it asks us to do is calculate heat transfer of the air into the reheat section. So I'm going to go through this relatively quickly because I think you're probably getting the hang of it by now. Conservation of energy looks like that. Steady state, Q reheat goes in, no work, no power. M dot air times mixture enthalpy at 2 minus M dot air mixture enthalpy at 3. Again, those enthalpies are the mixture enthalpies, air and water combined, divided by the mass only of the dry air. Solving for Q dot reheat, I have that, and H2 and H3 both are known because I fixed the state point at 2 with a humidity ratio and a relative humidity, and I fixed the enthalpy at state point 3 with a dry bulb temperature and a relative humidity. When all is said and done, you get just a little under 1,000 kilojoules per minute.